Statistical Learning in R here. And we are in the applied questions, and we're on question 5. And it's a big, long one. And so we'll look at them one at a time. But roughly what we're going to do is we're going to generate some data with that code block right there. And it's going to create a very unique pattern. And then we will try to classify those points with logistic regression, as well as a nonlinear support vector machine, and just kind of compare the results. So I have already ran all of this code, and that's important because depending on which random run of numbers you get here, part E and F want you to find a nonlinear boundary with logistic regression. And sometimes it's just kind of luck of the draw of what you get here. Sometimes you'll get something that looks linear, and sometimes you'll get something that looks nonlinear. And so I have a sample up here that looks nonlinear right now, and so I won't mess with rerunning it as we go. Okay, but here's the data, and I'm just packaging it into a data frame that I'm calling D. And then in part B, we're going to plot these observations. Okay, and so here's what the observations look like. Right, you see this kind of interesting pattern here, where, as you look at it, there's kind of maybe two boundaries going on here, two kind of linear boundaries, but it's not that if you go along one direction or the other, you see a predictable response in the outcome, and the outcome is here coded by color and the shape of the markers. So in part C, we're going to use logistic regression with x1 and x2 as predictors, and I take that to mean using them additively. So we're just adding these together in our linear model. Okay, so they're just two predictors. In other words, no interaction terms or anything else in there. And then we're going to make predictions from that model to see how they map back onto what actually is the case. Okay, so we need to find. So remember, logistic regression gives you values that kind of act like probabilities, go from 0 to 1, and so then we need to pick a threshold, and a great one here would be 50%. So if it's greater than 50%, we're going to say that that the model is predicting 1 and 0 otherwise. And then we just look at the consequences of that. Okay, and this is what is predicted then from the output of the model. Okay, and so again, this is supposed to represent the data, and it's not doing a great job. Okay. Now in part E, we're supposed to make a nonlinear regression, logistic regression. And you can do this in a lot of different ways, and I just simply chose to introduce an interaction term between x1 and x2, right? So up here in the linear one, I just use the plus sign for x1 and x2, and here I'm using the multiplication sign, which introduces an interaction. But again, the question gives you a lot of different ways you can make a nonlinear regression. I'm just choosing the simplest kind here. And then we're going to do the same thing. We're going to find the predictions and plot that, and this is what we get. Okay, and so in this particular case, again, it's not doing a great job, but there is at least a nonlinear decision boundary, right? If I kind of blur my eyes a little bit, this decision boundary kind of seems to bend as we go along here. Okay, and again, depending on the run of the data, you'll get different patterns here that sometimes look more or less, nonlinear. And so what we're seeing here is that this is not doing a great job. And I suppose, I didn't try this, but we could maybe come up with some monstrous set of prediction variables here that would eventually do okay, but then you might begin to guess that its out of sample accuracy may be horrible, just because of the complexity of the regression equation. Okay, so now we're going to fit a nonlinear classifier of a support vector machine, and see how that does. So we need to install and load the E1071 package, okay, which I've done here. And so the question asks us for a nonlinear classifier, but just, I guess, out of curiosity, I'm also doing a linear predictor here, okay, as well as a nonlinear predictor here. Okay. Now, in both of these, notice that I'm using the tune function rather than the SVM function, because the tune function allows me to try a bunch of different cost functions and a lot of different gamma functions, which are, kind of controlling, some of the parameters for the SVMs here. I think we kind of talked about that in the previous video, or you can just look at the help file to get a little bit more understanding of what's going on there. But it's trying different ones, and then it picks the best model, right? So we can just pick the best model from that, and that's what I'm doing here. So let's first look at the linear classifier, and predictably it's not doing good because, again, our data is not linear. Okay, so it's not doing great, and so you can see how many misclassifications there are. But now when we use the radial basis, it does pretty good. In fact, I think this one only has just a handful of misclassifications. So anyway, so that's the end. Part H, we're supposed to comment on our results. I don't know. Nonlinear SVM does good. I don't know, but you can put your own comments in there. Okay, we'll call that good.